In this video, we're going to look at an introduction to complex numbers. We are going to talk about how to graph complex numbers, find the absolute value of a complex number, and then some examples of how to convert between a complex number in standard form and trigonometric notation. So the first thing we're going to look at is how to graph complex numbers. We graph a complex number, a plus bi, in the same way that we graph an ordered pair of real numbers, x comma y, but on a complex plane. A complex plane has a real axis instead of an x-axis and an imaginary axis instead of a y-axis. So in looking at a complex number, a plus bi, a is the real part and b is the imaginary part. So now let's look at the following examples. We want to graph 2 plus 3i. So here a equals 2 and b equals 3. As I said, our x-axis is our real axis and our y-axis is our imaginary axis. So if we want to graph 2 plus 3i, we're going to go 2 points over on our real axis and then 3 points up, 1, 2, 3, on our imaginary axis. So now this is the point A. Looking at B, we have negative 2i. So here a equals 0 and b equals negative 2. So if a equals 0, as the same as if x equals 0, we're not going to move left or right on our real axis, and then we're going to move down 2 on our imaginary axis, and this is point B. For C, we have a equals negative 3 and b equals negative 4. So we're going to go 1, 2, 3 spaces to the left on the real axis, and then 1, 2, 3, 4 spaces down on the imaginary axis, and that's going to give us point C. For D, here we have a equals 6 and b equals 0. So we're going to go to the right 1, 2, 3, 4, 5, 6. And again, just as we were graphing an ordered pair, when we have b equals 0, we do not move up or down because the imaginary axis is 0. And that's going to give me point D. All right, now we're going to look at the absolute value of a complex number. The absolute value of a real number is the distance from 0 on the number line. So the absolute value of a complex number is the distance from the origin in the complex plane. And that's found by this equation right here. The absolute value of a plus bi equals the square root of a squared plus b squared. So now we're going to look at one quick example. We have negative 5 minus 2i. So again, a equals negative 5 and b equals negative 2. So we have the absolute value, a plus bi, is going to equal the square root of negative 5 squared plus negative 2 squared. And negative 5 squared is 25. Negative 2 squared is 4. So I get the square root of 29. So now we're going to look at trigonometric notation. If we let z equal our complex number a plus bi, where the absolute value of z equals r, let theta be an angle in standard position whose terminal side passes through the point AB. So kind of like we did on the graphing page, we've gone over a distance of a on our real axis, and then we've gone up a distance of b on our imaginary axis. And as I said on the previous slide, this distance from the origin is the absolute value of our complex number, and we let that equal r. So using this picture I have over here and the definition of cosine and sine, we can derive our trigonometric notation for complex numbers. So if the cosine of theta equals adjacent over hypotenuse, our angle theta is here, so adjacent is going to be A over R, and then sine theta equals opposite over hypotenuse. So again, looking at our picture, our opposite is B over our hypotenuse R. We're going to now solve this one for A and get A equals R cosine theta. And then we're going to solve this one for B and get B equals R sine theta. And then we're going to substitute both of those things into our complex number A plus BI. And we're going to get R cosine theta plus R sine theta I. And I can factor out that common factor of R and get R times the cosine of theta plus I sine theta. And this is going to give me my trigonometric notation for a complex number. And note that this form, A plus BI, is called standard form. All right, let's look at our first example. In this example, we're given a complex number in standard form, and we want to find the trigonometric notation for this complex number. So we have A equals -5 and B equals 5. All right, so as I said on the previous screen, R is the square root of A squared plus B squared, and we found that by using the Pythagorean theorem. So we have R equals A squared, which is -5, plus B squared, which is 5. So we have R equals the square root of 25 plus 25, which equals the square root of 50. And I can simplify that and get 5 square root 2. So now we have R equals 5 square root 2. So the next thing that we need to do is we need to find theta. So we know that cosine of theta equals A over R. So cosine of theta equals -5 over 5 root 2. My 5's are going to cancel out. I'm going to be left with -1 over the square root of 2. But we don't want to leave that square root of 2 in our denominator, so I need to multiply both the denominator and the numerator by square root of 2. And I get cosine of theta equals -√2 over 2. So my theta needs to equal cosine inverse of -√2 over 2. And then I also have sine of theta equals B over R. So I have sine of theta equals B, which is 5, over R, which is 5 root 2. Again, my 5's are going to cancel out, and I'm going to be left with 1 over square root 2. And doing as we just did before, multiplying both the numerator and the denominator by root 2, I'm going to get root 2 over 2. So I'm looking for a theta that equals sine inverse of root 2 over 2. So I'm going to go to my completed unit circle, and I'm going to look for theta equals a sine inverse of root 2 over 2, or a y value of root 2 over 2, and a theta where I have a cosine inverse of -√2 over 2, or an x value of -√2 over 2. So going to my completed unit circle, looking for an x value of a -√2 over 2, and I find that at 3 pi over 4 and at 5 pi over 4. And that's why you needed to do both of these, both the cosine and the sine, in order to know exactly which one we're looking at, and we needed a positive y value of root 2 over 2, and that only happens at 3 pi over 4. So that tells me that theta equals 3 pi over 4, or theta equals 135 degrees, depending upon if they ask you for degrees or radians. So now finally I can put it in trigonometric notation. I have negative 5 plus 5i equals r, which is 5 square root 2, times the cosine of theta, which is 135 degrees, plus I sine of theta, which is 135 degrees. So now I have it in trigonometric notation. All right, so looking at our last example, this time we're going to go the other way. We're given a complex number in trigonometric form, and we want to find the standard notation a plus bi for the following. So here we're given r equals 6 and theta equals 120 degrees. So we need to figure out what a is. Well, a equals r cosine theta. R is 6 and theta is 120 degrees. So again, looking at my completed unit circle, the cosine of 120 degrees is negative 1/2. So I have a equals 6 times negative 1/2. So I get a equals negative 3. Then we also need to find out what b is. B equals r sine theta. R is 6 and theta is 120 degrees. Going to my completed unit circle, the sine of 120 degrees is square root 3 over 2. So I have b equals 6 times the square root of 3 over 2. So I get b equals 3 square root 3. So writing this in standard form, I get a, which is negative 3, plus b, which is 3 square root 3, I. So that's really all you need for your introduction into complex numbers. Remember our equations. A equals r cosine theta and b equals r sine theta. Remember the difference between standard form, which is a plus bi, and trigonometric form, which is r times cosine theta plus I sine theta.